The half bridge converter, like the push-pull converter, is also a buck-derived converter where the secondary side of the half bridge converter transformer is center tapped and behaves exactly like that of the push-pull secondary stage. The only difference comes in the primary side. So let us consider where the half bridge converter differs with respect to the push-pull converter. I am drawing here a sine source, AC source, a rectifier and a capacitor filter. This is the AC to DC conversion where you have AC source, you have a rectifier and a capacitor filter. This we have studied, but I want to make use of this. I am showing this in gray shade. I will remove the capacitance and split the capacitor into two capacitors, and I will have balancing resistance there so that the voltage division is proper. Capacitances being equal, you can expect VDC by 2 to be across the top capacitor and another VDC by 2 across the bottom capacitor. So if you use this as the DC link for the switched mode converter circuit, the half bridge configuration looks like this. So I pull this out and call this one as VDC, and I will put this half bridge arm like this. So you have two transistors or MOSFETs or IGBTs in this fashion, and across the center here, this is VDC by 2 point, and we will put across the center a winding, and this winding of course the primary of the transformer. Secondary of the transformer is center tapped, and you have two diodes in this fashion, just like in the case of the push-pull, and with respect to the center tap you have this inductor and the capacitor and the output load. So behavior of the secondary side of the circuit is exactly same as the push-pull. So I'm just putting in freewheeling diodes, body diodes across the switches for completeness. You have the dot polarities in this fashion, and this is the pole voltage VP. So let us say you have 1:n in this fashion. L C V naught is the output voltage. So let us say when Q1 is on. So when Q1 is on, VDC is connected to the dot end. So dot end is positive with respect to the non-dot end. Non-dot end is connected to VDC by 2. So what you have here is plus minus in this fashion. Dot is plus, dot plus, and non-dot end minus, and the amplitude across the primary is VDC by 2 because this is at VDC connected to VDC, and the non-dot end connected to VDC by 2. So totally you have VDC by 2 appearing across the primary. This transfers to the secondary n times, so you have n times VDC by 2 on the both halves of the center tapped secondary. Now the dot end is positive, so this diode here, the top diode will be active and the bottom diode is reverse biased, and VP will be n times VDC by 2. So likewise we can also evaluate for Q2 on, that is Q1 is off and Q2 is on, and during this time you see that the dot end is pulled to the ground and the non-dot end is connected as usual to VDC by 2. So let us mark. So the non-dot end is positive, dot end is connected through Q2 to ground minus. So non-dot end is plus, dot end minus, like this. So if we measure across the primary, you have minus VDC by 2 appearing across the primary, secondary. Likewise, VDC n times VDC by 2 and n times VDC by 2 here with the polarity as shown. This diode, the bottom diode, is active, and VP is again seeing n times VDC by 2 just like in the push-pull case. All other operations on the secondary is same. You have periods of time when both Q1 and Q2 both are off. Under that condition, L is freewheeling through the secondary, equally dividing between the top half of the center tap and the bottom of the center tap. The MMFs cancel and d phi by dt is 0, and you have voltages across all coils being 0, at which point the center point is at VDC by 2 and the voltage that is across both the halves across both the switches will be VDC by 2. So therefore Vp is equal to 0 when Q1 and Q2 are off. And what is V0? V0 is related to the Vp voltage, which is equal to N times VDC by 2 into 2D. Here again there is an ORing effect here. The D is the switching, the duty cycle of the switching of the switches in a period Ts, but because the ORing effect, Vp waveform has a period of Ts by 2, and therefore the duty cycle of Vp waveform is 2D. Now I will put that 2D here. 2 and 2 will cancel off, and then you have V0 is equal to NVDC into D. So V0 is equal to NVDC into D is the input-output relationship for the half-bridge converter. Here one important point to remember as in comparison to the push-pull is that in the case of the push-pull, we saw the voltage across the device. You see the voltage across the device is on whenever the switch is on, and when the other switch is on, complementary switch is on, you see 2 times Vi coming across the switch. So whenever both the switches are off, you will see Vi coming across it. So the maximum voltage that each switch has to support is 2 times Vi. In the case of the half-bridge converter, the voltage across each of the switch max is VDC or Vi. So when the bottom switch Q2 is on, then you see that this point, the dot end point, is at ground, and therefore Q1, which is off, will have to withstand VDC. In the case when Q1 is on, you will see the bottom switch is off. Then this point here, dot end point, is at VDC, and Q2 will have to withstand maximum VDC. So that is the difference. The push-pull, the devices have to be rated twice VDC. In the case of the half-bridge, the devices have to be rated at just VDC. So you have half the voltage rating requirement for the half-bridge converter. That is an advantage. Another problem in the half-bridge converter, like in the case of the push-pull converter, is that of flux walking. You will see that in the case of the half-bridge converter, the primary side is not center tapped but a single winding. So let us look at the flux walking problem in the half-bridge converter. So let's say this is the V primary voltage across the single winding in the primary, and let us look at that primary voltage when Q1 is on and Q2 is on. So V primary is equal to VDC by 2 minus VC sat 1 when Q1 is on. See, normally when Q1 is on, VDC comes to the dot end and the non-dot end is connected to VDC by 2 here at the midpoint of the capacitance. So the voltage across the primary, V primary, will be VDC by 2. But in a practical case, because of the drop across Q1, you will see VDC by 2 minus VC sat 1 coming into the picture. Now, the other condition when Q2 is on, Q1 is off. So when Q2 is on, you will see that the on-state drop of Q2 comes into the picture, and therefore VC sat 2. And we know that VC sat 1 and VC sat 2 is not same, is not matching, it will not be equal in a practical case, and therefore there will be a difference between the primary voltage when Q1 is on and the primary voltage when Q2 is on. And because you are applying DTS for Q1 and DTS on time for Q2, the difference between VC sat 1 and VC sat 2 will reflect in an average primary voltage, very small average primary voltage. And because of the Faraday's law, V average, which is equal to N d phi by dt, phi, when you integrate the voltage, phi will be proportional to time t and it will gradually increase. So as a consequence, you will see that the average flux will start rising and then ultimately reach the saturation flux limit and saturate the core of the half-bridge converter. So how do we solve this? Like in the push-pull converter, we can use the same method of adjusting the duty cycles of Q1 and Q2. In the case of the push-pull converter, we had two sense windings, one sensing the Q1 part of the volt second and the other sensing the Q2 part of the volt second, and these two were subtracted. The error, the difference E, was passed through a PI controller. The output of the PI controller developed a correction voltage, and that was used for correcting the DTS or the on times of Q1 and Q2 respectively in such a way that E becomes 0, and if E becomes 0, then the volt second of the top part, that is when Q1 was on, and the volt second of the bottom part when Q2 was on would match, and thereby achieve the zero flux average and thereby avoid flux walking. Now this technique can also be used for the half-bridge converter, and the Q1 and Q2 duty cycles can be adjusted. In the case of the half-bridge converter, there is yet another way to achieve this achieve solution for the flux walking problem. That is by placing another component, that is placing a capacitor in series with the primary winding. The advantage here is that the primary voltage across the center tap here, if it develops an average, it can drop across the capacitance. There are two components here. The coil cannot withstand an average value, but the capacitor is capable of having an average value, and therefore the average value will drop across that and thereby save the coil from having any average. And this way the flux in the core will not walk away and the flux will not saturate. So this is a nice solution, and this capacitor is called the flux walking capacitor, CFW. Normally the CFW is rated for around 10% of VDC, though the voltage that comes across the flux walking capacitor will not be so high, it will be much lesser. One thing that one should remember is that the CFW, the flux walking capacitor, should be bipolar, should be capable of having current flow in both direction and the voltage in both direction, voltage drop in both direction. And another aspect is that the entire load current will flow through the flux walking capacitor, and therefore the RMS rating of the flux walking capacitor must be high, and this will make the flux walking capacitor costlier. However, this is a nice solution, especially if it is for low power circuits.